Okay, so last time we talked about cross-validation and prediction error when we apply our regression models. So I want to begin today by giving you some further comments and notes about how we can apply cross-validation in practice. Okay, so last time we talked about cross-validation, abbreviated with CV. Okay, so I still have this schematic laid out here, where we are taking the available data that we have for training and validation. Okay, and we divide it into k chunks. Okay, so each of these chunks is roughly equally sized. Okay, so in fold 1, we treat this first set as validation, and then we train on everything else. And then we evaluate the fitted models on the validation set, and we can calculate things like root mean squared error. Okay, so remember the idea is to use this cross-validation scheme and help us determine what are the best models that we can use in practice. When we then take our fitted model and apply it to new data, which we don't get to train or validate on, and we want to get the best predictive performance possible. Okay, so last time we introduced that idea, and I want to fill in now some of the details about how to actually do this in practice in some practical points. Okay, so today, CV in practice, and some comments on usage. Okay, so last time we assumed that we have say we have a few models to choose from. Okay, so let's first make this point. So given some models to choose from. Okay, so let's call them candidate models. Okay, so for example, in the demo. So in our quick demo last time, I just sort of picked 3 models. I called them M1, M2, and M3, and we looked at the validation average validation error. Okay, so if I already have a few models in mind, then I can use the estimated, for example, the estimated mean square prediction error to select one of those. Okay, so given some candidate models, for example, let's say we have a few with different variables included. Okay, so we can do say k-fold cross-validation using each of them. Okay, and then we choose the one with the lowest average prediction error across the cross-validation folds. Okay, so choose the one with the lowest average prediction error across the validation, across the folds. So, for example, if we're using root mean squared error, then we could calculate, for example, 1 over k. Little k goes from 1 to the number of folds, and then we average the root mean squared error calculated on the validation set k. Okay, so remember in fold k, this is using fold k as a validation. All right, so that gives us a procedure for choosing a model among several. Okay, so there's a couple of unanswered questions here that we need to look at a little further. Well, first one is, well, how many folds? Okay, so that's this value cap k. Okay, so how to choose the number of folds? Okay, the number of folds. Okay, so I would point out in our demo last time, we just did 5, okay? So 5 is a common choice. 10 is also a common choice. And you can also even take the number of folds to be equal to the number of observations we have. Okay, so let me, okay, so some common choices. Okay, so you could do, so last time we tried 5 folds, you could do 10 folds. You can even do, okay, so you can even set, for example, k equals n, where n is the number of observations we have overall for train validation. Okay, so this case of taking cap n folds essentially treats each observation. So if you're dividing it into the number of folds is the same as number of observation, that means each fold has exactly one observation. So basically, what that means is our validation sample for that particular fold only has one observation. It's the one that we left out. Okay, so this is also known as leave one out cross validation. Okay, so let's just put in here. So here the validation is just one observation. Okay, so this is also known as leave one out. Okay, so many choices for a number of folds. So how do we decide? Well, as a general rule, you can think of there's a couple considerations. Well, one is compute time. So of course, if you do more folds, you have to fit the models more times. Okay, so you'll have to do more. We'll have a higher computational cost as we increase k. Okay, because remember that we have to fit each model capital K times. Okay, so as we go down and use more folds, we know that we have increased more folds. You have higher compute time because you have to fit more models. Compute time. And secondly, well, but then there's clearly, I mean, there's a trade-off here. When you have more compute time, theoretically at least, when you have more folds, you also get a better estimate of prediction error if you were to then use the model on new data. Okay, so higher compute time, but can also give a better estimate of what prediction error will actually get. Okay, so that's a comment about the number of folds. Okay, so that's one consideration. Okay, now the next consideration is, well, how do we get candidate models? So in our first demo, we just selected a few models, just pulled them out of thin air without many model selection. So we already have a bunch of models that we're asked to compare. Then we could simply apply this framework, choose a number of folds, and then apply the procedure. But often in practice, we don't know what are good candidate models to try. So let's comment on this point as well. Okay, so this the question here is, what if we are not given Okay, and often this will be the case in practice because we are often instead just given a data set with many variables, and we might initially have no idea, well, which models should we even compare. So this should remind us of something we talked about a little earlier, which is the idea of model selection. So we know, for example, if there's a lot of potential predictors, okay, so especially and if there's too many variables, to do all possible regressions. Okay, so then what's new here is we now need to combine what we learned last time, which is cross-validation, with what we learned a while ago, which is on model selection. Okay, so the key idea here is then we can combine cross-validation with model selection procedures. Okay, and so remember when we talked about model selection procedure, we need a criteria, okay, for selecting which model based on the training data. And then remember we also have a search strategy for which models to check. Okay, so what have we seen so far in terms of criteria based on the training data? So in this context, it is highly recommended that we do our criteria based on the training data, because when we start peaking at the validation, that could bias our results. So for example, criteria that are based on the training data include things we talked about like AIC and BIC. And in terms of search strategy, we have seen things like, for example, stepwise. Okay, and so we know how to do that. So if I give you a particular training data set, we know how to carry out model selection procedures on the data set. So we could, for example, do stepwise regression and then choose some criteria that we can evaluate on the fitted model, like BIC. Okay, so how do we then combine that with cross-validation? Okay, so let's briefly discuss that now. And after I discuss that, I want to take a little rabbit trail to tell you about a few extensions of both criteria and search strategies, especially when the problems are fairly high dimensional in the sense that there are many predictors to choose from. Okay, but first let me summarize the strategy. So where we combine cross-validation with model selection. Okay, so when we talked about when we had a specific, like say M1, M2, and M3, and we use this framework, then we can easily choose one of the models. So now instead of choosing a model directly, we use cross-validation to choose the models, our model selection procedure. Okay, so let's describe that next. Okay, so that reviews model selection, and so now to estimate the prediction error for a given model selection procedure, Okay, and so you can compare this with, I wrote a very similar sentence last time when we were given specific models. Now let's suppose we're given model selection procedure. Okay, so that's the key difference. Okay, so you can compare with, after we finish writing the sentence, later you can compare with the corresponding one when we have specific models. Okay, so now we're extending the framework a little bit. Okay, so I'm going to mimic that sentence, but I'm going to apply it in the sense of using cross-validation to choose model selection procedure. Okay, so we apply it k times, okay, once per fold. Each time treating the observations in fold. Okay, so you have k folds, so 1 to up to k as validation sample. And then, just like before, we can then use for example, the average RMSE. Okay, so same formula. Okay, so we apply it k times, and choose the model selection procedure. With the lowest prediction error. Okay, so to finish that sentence, choose model selection procedure with the lowest estimated prediction error. Okay, so on one level, it's pretty similar to what we said before if we're comparing models directly. Okay, so instead of now estimating prediction error for specific models with specific predictors, we can do the same with different model selection procedures. Okay, so now one kind of interesting observation here is that the model selection procedure is not guaranteed to give us the same set of variables in each fold. For example, we do stepwise regression on fold 1, okay, so that might lead to a slightly different set of variables compared to doing stepwise regression on fold 2. Okay, so let's make a note of that first. Okay, so compared to so let's make this note. So compared to when we were dealing with specific models, note that in this case it's possible to have different. Okay, so note. Okay, so note that the actual variables selected in each fold could have some differences. Might be different. Okay, and that's in fact quite likely to happen when we have a lot of predictors. Okay, so we're trying to find the strategy that gives us the lowest prediction error, but then within each fold, that doesn't guarantee we actually have the same set of variables. So usually what we recommend at the end then is we then apply the entire model selection procedure on the entire data set once we've settled on one, and then use that as the representative final model. Okay, so the recommendation is to then apply the chosen model selection procedure Okay, so the one that's chosen is the one that has the lowest estimated prediction error. Okay, with the lowest estimated prediction error. And so apply it to the entire set of observations available for training and validation. Okay, so the key here is we're applying the procedure to get a final model. To get a final model. Okay, and then we can apply that final model then in the future for test data. For applications to test data. Okay, so where we actually have to do prediction. Now, why do we suggest refitting the model, applying the same procedure to the entire data set? Because now we have settled down on the best selection procedure, and so now at the end it makes sense to use all of the data to select the actual variables to include. Okay, so that's the gist of how we can combine cross-validation with what we've learned previously in terms of model selection procedures. Okay, now in practice, right now are the tools that we have for model selection. We have, for example, one model selection procedure. We might do, for example, forward stepwise regression with BIC. Right, that would give us one way to estimate models and calculate prediction error, and then maybe a computing selection procedure might be to do stepwise regression with AIC, right? So you could change these two components to come up with different model selection procedures, and then choose the one that's the best. So for example, if stepwise with BIC turns out to be the best procedure, then we can take stepwise and BIC. If it does the best on the cross-validation, we can then apply that to the entire data set to come up with a final model to use for future prediction. Okay, so that's the key idea here. All right, so let's talk a little bit more about. So I want to give you a little the gist of some potential other extensions of these sorts of criteria and search strategies. Okay, so to preface that, I mean, our university is said to, we want to go, beyond ideas and beyond disruption and all that stuff, whatever it means. So I'll call this procedure. So what I'll call this little segue is, well, if we want to look at things that we can do other than just plain old AIC and BIC, so let's call this beyond AIC. Okay, so just to give you a couple ideas of other metrics that could be useful. All right, so here we go, beyond ideas. All right, so AIC and BIC, if we recall, so it looks like this. So AIC is 2 times, remember Q is the number of model parameters, and then we do minus 2 ln of the log likelihood at the parameter estimates. Okay, so just to remind you of that. And then we have BIC, which is 2 times ln of n, so it's a different penalty, remember? So remember AIC and BIC, they penalize having too many parameters, so these are two choices of, two specific choices of penalty terms. Okay, and so so there are many other extensions, but I do want to mention one that's that we can explain easily, given what we've learned, and is still quite useful. Is, well, I mean, these are the, okay, so these guys are the, sorry, there's no 2 here, so let me get rid of this. Okay, so the penalty for AIC is 2 times the number of parameters, that should be Q actually. And then the penalty for BIC is the number of parameters times the log, so it scales with the number of observations. So a natural extension to that is to, for example, we can impose arbitrary penalty on here. So for example, we can do Q times, so let's just put some penalty parameter here, let's call it lambda. Q times lambda minus 2 log likelihood. Okay, and so what this is called is this is extending AIC and BIC to using a sort of a generic arbitrary. What this is in technical terms, this is a general L0, what we call a L0 norm penalty, because it penalizes you for having more parameters. So every time you add a parameter, we add a penalty, a corresponding penalty lambda. Okay, so this is the general name for this is L0. We can call it L0 penalized likelihood. Okay, and so AIC and BIC are specific forms of it. Okay, so each of them include the log likelihood part, and then it penalizes you for having more parameters, and this is one way to prevent overfitting. Okay, and then we can treat lambda as so we can treat, for example, stepwise regression with different values of lambda as different model selection procedures. Okay, and then we can try different values of lambda to construct new model selection procedures. Okay, so in the language of statistical and machine learning, this guy is, you can think of this as a tuning parameter, and so tuning parameters are especially, methods with tuning parameters especially work well with cross-validation. So for example, we could do stepwise regression with lambda equals one number, and then do stepwise regression with lambda equals another number. So how do we decide which lambda is better? Well, that's where cross-validation comes in. Okay, so you can see how this is related to what I'm talking about here. Okay, so we could do lambda equals 100 with stepwise forward, and then we could do lambda equals 50 with stepwise forward, and those would be two different model selection procedures, and then we could use cross-validation to figure out which lambda actually works better, for instance. Okay, so there are many extensions like we could talk about, but this is probably the simplest one that I can relate to some existing things that we've seen. Okay, so this is a generalization of AIC and BIC. Why do we call it L0? So there's also corresponding penalties that use L1 and L2 norms. You want to be technical. So L0 basically is just counting how many parameters are used in the model, and using that in the penalty for the penalty part of the log likelihood. Okay, so that gives us a few more things in our toolbox that we can use for testing different model selection procedures. Okay, so that's the first extension. Is we can modify AIC and BIC to use an arbitrary L0 penalty term, and then we can choose the value by using cross-validation. Okay, so that's the first part of Beyond Ideas, and the second part is, well, what we learned was stepwise regression. So let's do Beyond Ideas for stepwise regression. Okay, so I'm going to again just give you one example of an extension that can be more effective. So all that I'm telling you here is just tip of the iceberg in terms of the kinds of things that researchers have come up with as a way to do better than simply the classic criteria and stepwise regression that we've seen. Okay, so if you're interested in this topic, of course, you can use this as a launching point to look up more materials. But for now, I just want to give you some more things in your toolbox that you can consider using, especially, for example, for your project. Okay, so beyond stepwise regression, so I'll just give you one example of how to search stochastically. Okay, so remember that stepwise is a deterministic algorithm. Okay, remember each time if we're doing forward, we just pick the best predictor, add it to the model, then we do it again, take the best predictor, add it to the model. And so we're given the same data set. Every time you run stepwise, you get exactly the same answer. Okay, so it's a deterministic algorithm. We pointed out it's fast, but it doesn't guarantee that we get anywhere close to the best model, especially if there's a lot of predictors. Okay, so this is a deterministic algorithm, and which is fast, but might not give an optimal model selected. Okay, so I'm going to give you one basic extension to that, and there are many I could talk about, but I'll just choose one for today. Could try stochastic algorithms. Okay, and so I'll give you one today, which is called iterative conditional minimization. Okay, so I'm going to abbreviate that as ICM. So it includes some randomness in the search process, so as to potentially give us a more optimal solution. So it still can't guarantee the best model. So this is still the only way to guarantee that is all possible regressions or a more clever way to do that. But this is still pretty fast in general, but can give us a potentially better solution than simply just doing the plain old stepwise. Okay, so I just want to give you an overview of this algorithm. Okay, so we've talked about that. Okay, so let me just give myself a space. Okay, and so one of the intuitions for using stochastic algorithms is each time you run it, so with a different random seed, you could get a better solution. So you could run it multiple times and pick the one that gives you the best criteria. Okay, so here is ICM, just to give you a sense of what this sort of algorithm could look like. Okay, so this should be, pick this one, it's pretty easy, pretty intuitive, and pretty easy to explain. Okay, so what we do is, for a random seed, so we first, we start with an empty model. Start with model with just intercept. Okay, and then for a given random seed, so pick a seed. What we're going to do is randomly order all the predictors. So take the predictors. So let's say they're x1 to xp. And randomly permute them. So randomly reorder them. Okay, and then we'll call the randomly reordered version. Let's call it x. I'm going to put a bracket here. Okay, so to indicate these are reordered. So they're all the same variables, but they're just in a different order. Okay, so that's where the stochastic part of the procedure comes into play. Is you choose, you randomly order these predictors. Okay, and now we do something that's pretty similar to these sorts of stepwise methods, where at each operation we either add a variable or we delete a variable. Okay, and we can do it in this way. Okay, so we cycle through the predictors. Okay, and so at each point, well, each of these predictors will currently either be in the model or not in the model. Okay, so just to keep the notation, just to keep the description a little shorter, let's just call set S be the set of predictors currently in the model. Be the predictors currently in the model. So when we start at the start, S is just an empty set. Okay, so we'll go through all the predictors, and then so the intuition is very simple. So if that variable is currently not in the model, let's try adding it to the model, okay, and then see if that improves the criterion. And if that variable is already in the model, let's try taking it out and see if it improves the criterion. Okay, so it's pretty intuitive. Think of it as an extension of forward backwards in the way this procedure is constructed. Okay, so let's write it up. Okay, so if xj, so this predictor is not in S, and we try adding it. Okay, so if that's the case, then fit model with current variables with S and xj. So add xj to the current list of predictors. So try fitting that. And then if addition of improves the criteria, then add that variable xj to s. Okay, so now s has one more variable. Okay, so the flip side of it is if xj is already in the model, then let's try taking it out. And see if taking it out improves the model. Okay, so again, we can see some similarities with our forward-backward, except that we've introduced an element of stochasticity, and also, as we'll see, we're going to iterate through this process multiple times, and potentially get a better solution than simply doing it using the classical stepwise procedure. Okay, so if the variable is not, if the variable is currently in S, then let's try removing it. So fit model removing xj. And so if that improves the criteria, okay, and so if excluding xj improves the criteria, then remove xj from S. Okay, so that's the basic procedure. So you see it's a bit of an extension of stepwise. Includes this randomness. So we randomly. So this order is going to matter because this loop is going to depend on the order in which these predictors were rearranged. Okay, and so well, we just keep doing this. So there's 10 predictors. We go 1 to 10. Okay, so maybe after the first pass, we might have let's say 4 variables, and then we go through it again and again until no more changes happen. Okay, so this is a simple way of doing a stochastic search for the best possible model, and it's still much faster than doing all possible regressions. And there's a good chance, especially with a lot of variables, this can give us a better final model than just doing the plain stepwise procedure. Okay, and so repeat for loop until. So if you go through the entire for loop and nothing happens, then we're done. Okay, so there until no variables are added. Are added or removed. From an entire pass through the for loop. So that means we have converged given that particular ordering of variables. Okay, so that's an example of a simple stochastic way of searching for the best model. Okay, so notice here that if you use a different seed, this could give you a different set of this procedure could give you a different set of variables, and so each of them, of course, you evaluate the criteria. So you could actually run this algorithm multiple times with different random seeds, and then you find the one that has, for example, the lowest BIC, for instance. Okay, so note that different random orderings could give different sets of variables S at the end of the procedure. And so, well, you could then just simply pick the one that gives you the best criterion. You could pick the one that gives as the best criteria, overall criterion. Okay, so that's what I wanted to talk about as far as first telling you how we can combine cross-validation with model selection, and then giving you just a few extensions to model selection criteria, and also to giving you a stochastic flavor of doing an iterative kind of variable selection. So for the rest of today, I just want to give you a demo of these on the computer, and in particular, I want to do a data set with lots of predictors, so you can see how some of these things work out in practice, and especially want to show you how we can address things like overfitting using what we learned today. So I'll be with you on the computer in just a moment. Okay, so let's do the demo together. So the data set I pulled is from a recent paper on how to classify Haydn and Mozart string quartets based on various musical features. So this is the data set. Okay, so let's load it in. So you notice there are 285 string quartet movements in this data set, and there's a lot of features that we calculated from them. So these are summaries of various musical features of these quartets, so there's over 1,000 of them. Okay, so before we do anything, let's the first column is just the name of the quartet, so I'll take it out by setting it to null. And then, so what we have is 285 observations, and the data set has over 1,000 columns. Okay, so for our purposes, let's choose one of these variables as the response, just to illustrate these sorts of methods. Okay, so let's try to predict the number of notes in the violin part. And so that's this variable named called count pitch, and in the data matrix that's 683rd column. Okay, so we use that as the response. That means we have potentially over 1,000 possible predictors. Okay, so first thing to note is, well, so in this case there's actually more predictors than observations. So we cannot just fit a linear regression model without doing variable selection because x transpose x will actually not be invertible because you have more x will not be of full rank and is not invertible. Okay, so this is kind of a real world scenario that sometimes we'll encounter, that there are more potential predictors than observations. Okay, so let's illustrate these ideas I showed you. So let's try doing something beyond just AIC and BIC, and then let's also try ICM as a way of searching for models. Okay, so let's just define a few things. So this setup is very similar to that of last time. So we have let's call cap n the number of observations I have available. So that's 285. Okay, and I'm going to do some random stuff here. So let's set the seed so you can replicate this analysis later if you wish. Okay, so just here's set a random seed, and then just like last time, just to keep things simple for now, I would just do a single train and validation split. So put 80% in training, and then put the other 20% in validation. Okay, so first let's start with something we already know how to do. Okay, so let's try doing forward stepwise. Okay, notice in this case that we can't actually do backward elimination because, as mentioned, there are too many predictors, and we can't actually fit a model with all the predictors. Okay, so let's start with something that we know how to do, which is let's do forward stepwise, and let's use BIC as our criteria. Okay, so I'm going to define the full model and an empty model, and then start with the empty, and then start adding things one at a time. Okay, so I'm going to use this this stepwise command, which is pretty similar to what we've seen before when we learned stepwise regression. Okay, so I'm going to set the penalty term to be log times the number of observations, which is the penalty term for BIC. Okay, so I'm going to run that. And so, as expected, it will take a bit longer this time because each step in the stepwise, it has to check over 1,000 regressions. Okay, so you can see it is doing its job. It's adding variables one at a time. Okay, now you're starting to see there's quite a lot of variables being added to the model because the BIC keeps dropping as we add more variables. So you see, okay, I can't even count how many. There's probably like several dozen variables now. Okay, so let's let that run. Okay, so that's finished now. So the final model from stepwise is actually this really long formula. Okay, so this is the model that was selected by forward stepwise using BIC. Okay, so what I've done here is I've simply copied this model formula and called this M1. Okay, so that's just copy paste of this model found by stepwise regression. So let's fit it. Okay, we can look at the summary, for instance. And the thing I want to point out here is that this r squared, right? This multiple r squared is huge. It's almost 1. It's 0.9978. And okay, so if it's this high, you know, either we can actually predict the variable really well, or because we have a lot of variables, this could potentially be overfitting. Okay, so you remember last time we had this graph of where the model complexity increases, so we start adding more variables. Its ability to perform on the training data it can fit the training data very well, but that doesn't guarantee that will be generalizable to your validation set. Okay, so that's why we have a train and validation split. And so let's see how well this very complicated model with many predictors actually performs on our validation set. First though, one note about calculating penalties. Okay, so today I talked about how we can use different L0 penalties other than simply AIC or BIC. So this is how we could compute it. We can compute them using the AIC function. We just have to we can set our own penalty term in here, and then the AIC calculation will adjust for that penalty term. Okay, so here the penalty I used was log of the number of observations in the training set. Okay, so it's log n, which is the BIC penalty. So I can calculate it. So this is to show that I can calculate that using the BIC penalty, and I get 1977. Okay, and so because in this case the penalty was exactly the same as that of BIC, I can use the BIC function and it should give me exactly the same answer. Okay, so this just shows that we can use the AIC to calculate with any L0 penalty that we choose. Okay, so that illustrates that point. Now, let's actually evaluate how well this model does on our validation. Okay, so I'm going to use the same commands I showed you last time for cross-validation, and let's do the prediction. So we're going to predict on the validation sample, so that generates the predictions, and then I can calculate the RMSE on the validation data. Turns out to be 27. Okay, and remember, I can also calculate RMSE on the training data itself, which is simply to take the average squared residual. Okay, so remember the RMSE on a train is simply the sum of squares residual divided by the number of observations. So I can do the same thing on the training data. Okay, so it turns out that comes out to be 11.9. Okay, and so we see this this potential issue where the RMSE on the validation set is much larger than that on train. Okay, so remember, if you think back to the picture we drew last time, when the RMSE or the prediction error in general is much higher on the validation set, that suggests that perhaps we have overfitted our model, and it doesn't generalize well to new data, because we think based on the training data the RMSE should be pretty low, around 12, but it turns out to be much higher than that when we apply it to data that was not used to fit the model. Okay, so this shows, for example, we might want to increase the L0 penalties so that we favor more simple models with fewer predictors. Okay, but before I do that, let me also show you how we can do ICM. So use iterative conditional minimization to search for a model with potentially a better value of BIC. Okay, so notice here, according to the BIC function, we got 1977.6. So I'm just going to copy that here. So so we have that value. Okay, so I'm going to run ICM. So I'm going to start running it, and I'm going to talk about the actual code and explain how that works. Okay, so let that run. It's going to generate a bunch of output, and while it's doing that, let me talk you through what's actually happening. Okay, so first I'm just defining a penalty, because we might want to change it. Okay, to help control for the number of variables that we're going to include in our model. So first I'm just going to use the BIC penalty, which is log of the number of observations that we have for training. Okay, so I'm going to just define an empty list of variables. Okay, to start, and then so this is going to be a list of things that we have in the set S, and then just to help keep track of what's going on, I'm going to extract the names of the variables. Okay, so that's what's being printed here when I run the algorithm. Okay, so this is a key step, because what this does is I'm sampling I'm making a random order of the variables. Okay, so that's why I'm using the sample command, which I showed you last time. Okay, so this is the number of columns I have in terms of the variables I have. So I'm going to create a random ordering of that. Okay, so this is giving me a random order of the variables. Okay, and then I'm going to set up a a variable to help me track what my current value of the criteria is. Okay, I'm going to start by just setting it to be infinity because we haven't fit any models yet, and so we're going to anytime we improve on the criteria, we're going to use that as our most current model, right? Until we can't improve the criteria anymore. Okay, so this is just a trick, so then we can use it with the rest of the procedure. So once we have a model, then the minimum we'll start to have actual values for the criteria, and then we'll trace how that criteria improves as we add and remove variables. Okay, so another reason why it's this is a nice algorithm to show you is you can help give you a few more skills in terms of our programming. Okay, so I'm going to set this thing called no change, set to false to start. So basically, what I'm going to do is I'm going to use a while loop. Okay, so what the while loop does is, as long as this condition in here is satisfied, it's going to keep running. It's going to keep running this. It's going to keep running this loop. Okay, so what I want to do is I'm going to do my iterative adding and removing variables until no other changes are made to the model. Okay, so when I start this loop, I'm going to say currently there is no change, and if anything was actually changed, I'm going to set this to false. So then we'll run through the entire loop again. Okay, so that's how we can accomplish the goal of iterating through that for loop until there are no more variable changes. Okay, so now you can see I'm implementing with the pseudocode I wrote on the board. So I'm going to now go through all the variables in this random order. Okay, so in the order that was sampled. In fact, we can take a look at this order. Okay, so you see it's all the over 1,000 predictors arranged in random order. Okay, and so now we're going to loop through in that order, and we're going to implement those two steps. If the variable is not currently in the model, we try adding it to the model, and if it is in the model, we can try removing it from the model. Okay, so the reason I take out 683 is because that's the response, so we're not going to use that in this procedure. But otherwise, you can see this block, what it does is, so so you can read this as if the variable is currently in our set, and and if we have variables in our set, we try removing it. Okay, so this chooses the indices to include in the model fitting, and then we select the corresponding columns of our training set. Okay, and then we can fit that model. Okay, so the reason for that is because then we can use the standard LM syntax by just putting a period. So use everything in here to fit the model. And then we check the criteria. So for example, if we're using BIC, then we start with this penalty term. Okay, and that improves the model according to our criteria. So if it's better than what we currently have as the minimum value of the criteria, then we update our model to use the updated set of predictors. In this case, removing this variable. So if removing the variable improves the criteria, so that's this if statement, then we update the minimum criteria, and then we remove that variable from the current variable list S. Okay, so all I've done here is I'm just putting in a print statement, so you can actually see what's being done at each step of ICM. Okay, and so just to keep track of the best model, I'm going to call that the best model as the best one that's been found so far. So anytime I have an improved model, I update this this variable called best model. Okay, and so if we have changed something in the model, so I'm going to set no change to be false. So the next time we go through the while loop, it's going to run this whole thing again. Okay, and then on the flip side, we have if the variable is currently not in the list, that we can try adding it to the list. So this appends this variable to the current list of variables we have, and then we try fitting the model with that additional variable. And again, if that fitted model improves the BIC in this case, then we update the value of the best BIC found so far, update the variable list, and then I just print out what we have so you can trace what happens. Okay, so now let's scroll up so I can show you what's happening. So you can see it went through quite a bit of steps and took a bit longer than stepwise regression, but we can also see whether it found a better solution, for example, than stepwise regression. Okay, so this is where I ran the code. So we see that the first variable added was this one, recap 14.3, and this was the value of the BIC when I added that variable. Okay, and then as it's going through the for loop, it adds a next variable. Okay, the dev count, this particular variable, and you can see how the BIC is changing as I'm adding criteria. So often in the first pass in ICM, we tend to add a lot of variables. Okay, so we're going through and we're adding variables. You can see the BIC improving as we're doing that. Okay, so the variable list is getting quite a bit longer now as we're adding variables, going through that for loop. And so after one pass, it's going to go through again, and then now it's going to check whether we want to remove any of these on the second pass, and whether we want to add any other ones. Okay, so this is you can see this printing it out, it just shows what it's doing at each step. So every time it adds or removes a variable, I'm just printing out what the new value of the BIC is and the current list of variables in the model. Okay, and so you can as you scroll through, you can see the BIC continuing to decrease as it iterates. And so you do notice that the list of variables, it does expand and shrink as it goes through the iterations. Okay, and so let's go all the way down then and find, well, what's the best value of BIC that this procedure found compared to stepwise. Remember, in stepwise, the best value of BIC we found was 1977.6. Okay, so we see we were already doing better than that. As we were partway through this output, we already found a BIC value of 1861. So you see this stochastic way of optimization can indeed find a better model according to the criteria that it's given. Okay, and so we that process. Okay, so let's scroll all the way down and see what was the final model that it came up with. Okay, so this is the final model. It's this line here. Okay, and what it says is, in fact, it found a BIC of minus infinity. Okay, so what does that mean? So in fact, it did much better than stepwise. It found what is a perfect fit to the data. Okay, so let me show you what that is. So let's take a summary of the best model found by ICM. Okay, so what you notice here is this output looks a little strange to us because it has a whole bunch of NAs. It has a lot of variables, and ultimately what we see is that there is no residual standard error, and the R squared is 1. So literally we have fit all the data points perfectly. So in other words, ICM was able, using BIC as the criteria, was able to find a perfect fit of the data using a subset of the variables given. Okay, so in that sense, it accomplished the search quite a bit more effectively than stepwise regression. Okay, now, what's the key takeaway here is, one, that ICM can find a better model according to BIC, but what does that mean in terms of predictive accuracy? Okay, so let's try to do that. So let's use this model found by ICM, and let's use it to do prediction. So we already know that it fits the training data perfectly, which often in a problem like this is actually bad news. Okay, so let's look at the actual numbers. Okay, so I'm going to do use ICM and do prediction. Okay, let's calculate the RMSE on the validation set. Okay, and so what do we notice is we have a very large RMSE on the validation set. And on the other hand, on the training set, we already know it fits perfectly. So the RMSE is actually going to be 0. Okay, so we can verify that. Indeed, the RMSE is 0 on the training set and very large on the validation set. And we can compare that to what we got using the stepwise. Okay, so stepwise didn't find a very good BIC value because it's a very it is very restricted in terms of just adding one variable at a time. Okay, and so remember we had a stepwise RMSE on our validation data, which was 27, and on the training data was 11.9. Okay, so if you compare these, we notice that the validation RMSE went up a lot, which shows that using BIC with ICM as the search criteria, so that's using that as the model selection procedure, led to a very overfitted model. Okay, so we're doing very badly in terms of prediction on new data. Okay, so that this shows a huge gap between model performance in terms of prediction error on training data compared to the validation data. Okay, so that illustrates concretely what we mean by overfitting. Okay, so it does really well on the training data and does very poorly on the validation data. So that suggests that the model has too many variables, might be too complicated. Okay, so let's show you then the extension of AIC and BIC. Okay, so for example, let's try with a larger L0 penalty. Okay, so for example, this is just one example. Something we can try is I'm now using a larger L0 penalty, and you see here we're going to try stepwise again, but with a penalty which is like 2 times the usual BIC penalty. Okay, so I'm going to do stepwise regression again with a larger penalty. So larger penalty means that you penalize more strongly having more predictors in the model. So for example, using stepwise, it should give me a simpler model with fewer predictors. Okay, so this is one way to control for that, is to use a stronger penalty. Okay, so based on stepwise forward selection, but with a stronger L0 penalty, we notice we now have we end up with a much simpler model. In this case, we have 9 predictors. Okay, so the final model here has 9 predictors. So again, M2, I've simply copied this model formula into here so that we can do some of our own assessments. Okay, so let's fit this model and let's do some assessments on it. So first, for example, we can calculate the value of our criteria. So now, since we used a different value of the L0 penalty, I can manually type it in here. So I'm using twice the usual BIC penalty here, and I can calculate the value of this L0 based criteria. Okay, so it's 2187. Okay, so let's see how this model selection procedure performed. So let's do a prediction again on our validation set. So calculate the set of predictions and calculate the RMSE. Okay, so notice it does appear that it is smaller. So when we had the very complicated model, the RMSE was around the 27. Now it's a bit smaller at 23.8. Okay, likewise, the RMSE on train should probably be larger as well, because we are less likely to overfit on the data. And so indeed, the RMSE on the training is quite a bit higher. So in fact, these two values are closer, which is good news in the sense that it gives us evidence that the model is more generalizable. Okay, so I could do the same thing using ICM as the penalty. Okay, so I could use this. I could also do a stochastic search with this larger penalty for more variables. Okay, so again, I can just set this penalty term, for example, to be 2 times the usual BIC penalty, and I could do ICM with this larger penalty as well. Okay, so let's just run that, and so hopefully, since ICM is more generally comes up with a better solution according to the criteria, let's just see that we don't get a degenerate model. Okay, so that's a good sanity check. Okay, so in fact, it finished quite a bit faster, and the criteria was a more sane value. Okay, so we don't get a perfect fit or a heavily what would we expect to be a heavily overfitted model. The criteria seems pretty reasonable, 21, 28, compared to when we simply did stepwise. So this does find a better value of this L0 criterion. Okay, so remember our criterion based on stepwise regression, we found the best value is 2187, where lower is better. So ICM was able to find something of a better criteria, 21228. Okay, so again, more effective at searching than just plain stepwise. Okay, but let's actually see how well this model does. So let's use the ICM procedure model to make some predictions. Okay, and it turns out the RMSE on the validation is it's comparable to what we have. So that shows maybe this sort of this amount of penalty can give us reasonable performance on validation data. Okay, and we also check the RMSE on the training data, and it's probably going to be smaller because ICM did a better job of searching through the model space. So there is a bit of a gap between these, but again, we might need to do more replications and do these. And in practice, we can do these procedures within cross-validation to help stabilize and give a more stable estimate of these. So remember, this was just based on just a single training and test split. Okay, so I do want to demonstrate that to end off today. So we can apply different model selection methods within the cross-validation. Okay, so the setup for this is very similar to last time. So I'll just walk you through it. Okay, we're going to choose number of folds, just for instance 5. Okay, we're going to randomly allocate the available data. Okay, we're going to randomly set the indices, so about 1/5 is in each fold. And then let's just for the sake of illustration, let's compare two model selection methods. Okay, so let's compare just for simplicity here. Let's do stepwise with two different penalties as our two different competing model selection methods. So the only difference here is we have use stepwise with BIC, and then we can do another stepwise with a stronger penalty. Okay, so otherwise the rest of the setup is similar. So we divide within each cross-validation fold. We set up our training set, we set up our validation set. So it's basically repeating what we've done prior, just K for all K folds. Okay, so the rest of the code is pretty similar. So here is the model found by stepwise regression with this penalty, and then here's a model found by stepwise selection using this stronger penalty. And another one, and then we use that model to do prediction, and then we calculate RMSE. So this loop is very similar to the one we saw last class. And instead of fitting a specific model for M1 and M2, I'm now using a model selection procedure. Okay, so in this case, stepwise with this penalty 1, and stepwise with penalty 2, and then I'm comparing which one does better, which of these model selection procedures does better in terms of the cross-validation prediction error. Okay, so I can run this loop, and then I can look at the RMSEs over these two different procedures and look at their means to convince ourselves of which of these actually does better as an overall selection procedure. Okay, so this does take a little bit of a while to run. So I will tell you at the end of the result that you can try running this on your own. It does show that in this case, we will find that the model the model selection procedure that uses the stronger penalty does overall give a better prediction error. Okay, so based on this procedure, then, according to what we talked about earlier, we could then apply this stepwise procedure to our full data set to get a final model for applications to new test data. Okay, so I'll just put a note here. So it turns out M2 is the better procedure. Among these two, so we could recommend applying procedure M2 to the entire 285 observations. Okay, to get a final model. All right, so that is what I want to talk about today. So give you some additional tools for doing model selection and how to use cross-validation with model selection. Okay, so we covered quite a bit of stuff. So if there's any questions, I will answer them before I log off. Okay, and in the meantime, I can show you that we can start running this. I don't think it will finish necessarily in just a few seconds, but you can start to see what it's doing. It is taking each, so for each fold it is fitting models using these two model selection procedures, and so it's just going through the various stepwise procedures, and so at the end we can compare the cross-validation errors based on these two procedures to choose one of them. Okay, so in practice, of course, you could try other selection strategies. You could try even more variants of penalties, and so there's a lot of so the idea is to show you that there's quite a lot of flexibility in terms of how we apply a framework like this. Okay, so there's no hard and fast rule for what we should do. So often in real data applications, it does take a bit of trial and error and a bit of fine tuning in order to find a reasonably working model that can do well on both the training data and the validation data. And so in doing that, it gives us confidence that the model can generalize well when we apply it to data that we never see before, which we call the test sets. All right, so let's wrap up here for today, and remember to submit your third assignment. And once you do that, then you can focus your remaining work on the final project, and there will be one last quiz as well next week. So once you finish the assignment, then it's time to think about working on the final project, and perhaps applying some of these tools I've introduced to help you find a reasonable model for the project data set. All right, so we'll be back on stream on Monday.